Hello, so this video will go over exam 3, the study guide. Exam 3 is on chapter 8, 6, and 9, or 8, 9, and 6 in the order that we learn them. So this is the study guide. It's available in Canvas. And so the learning objectives for chapter 8. So let's start with chapter 8. That's the first one here. So these are the objectives about what you need to know from chapter 8. Identify the solvent and solute in a solution. So a solution is made of a solvent and a solute, and the solute is the component in the smaller amount, and the solvent is the component in the larger amount. So for example, if you have a solution of isopropyl alcohol at 70%. So it's isopropyl alcohol at 70%. So that's the solvent, and it would be 30% of water. So water would be the solute. You need to be able to classify a substance as a strong electrolyte, weak electrolyte, or a non-electrolyte. So a strong electrolyte is a substance that completely dissociates into ions in solution. For example, a strong acid or a strong base or a soluble ionic compound would form strong electrolytes because all the formula dissociates into ions, and it's a single straight arrow to the right. So here we are on a slide from chapter 8, so slide 15. So this shows a strong electrolyte. A solution of Na2SO4 would be a strong electrolyte because all the compound, the solute here, which is a solid, dissociates into 2 sodium ions and 1 sulfate ion. And you recognize a strong electrolyte because it has a single straight arrow to the right. It completely dissociates. And it dissociates into ions, right? Because you have a lot of ions in solution, it can conduct electricity. A non-electrolyte would be, for example, a solution of sucrose or glucose, which are organic molecules. Which are solid, and when you dissolve them in water, it's still the same molecule, but now it's separated from others, and it's surrounded by water, but it doesn't give ions. It's a covalent compound, so it stays bonded together, and it doesn't dissociate into ions, right? It's not an ionic compound, it's a covalent compound, so it stays as one molecule. And the molecule doesn't, the molecule doesn't have any charge, so it is neutral. And because of that, it will not be attracted by the positive or negative electrode. So it would not conduct electricity. So that's a non-electrolyte. And finally, below that is an example of a weak electrolyte. A weak electrolyte is a substance that dissociates partially in water. You see how we recognize a weak electrolyte by the double arrow that indicates an equilibrium. So you have the forward reaction, but also the reverse reaction happening at the same time. And typically you have more of the reactant in solution and fewer of the product. It depends. The equilibrium can be, favoring the product, favoring the reactant, or about the same. But for example, this is a weak acid here, and a weak acid only weakly dissociates. So you have very few ions in solution and more of the acid as a molecule without a charge. So that's why there is few ions and it's weakly conducting the electricity. There is not enough ions to fully conduct the electricity. So that's a weak electrolyte. You recognize it. So they do have ions, but it's an equilibrium, And typically the equilibrium is not in favor of the ions. So there is few ions that can only weakly conduct electricity. So next, like dissolves like. So this is an important solubility rule, a general rule. When you're looking at all kinds of substances, of covalent, ionic, and it allows you to predict which molecule will form solutions using the polarity of the molecule. And so like dissolves like means polar molecule will dissolve in polar solvent and non-polar molecules will dissolve in non-polar solvent. So the properties of polarity needs to match between the solvent and the solute for solubility to occur. So that's a general solubility rule. And then there are more specific solubility rules to help you predict if ionic compounds dissolve in water. So for this, you would use the reference packet. So page 3 of the reference packet, those yellow pages I gave you as references that you will have for the exam. So there is a table of solubility rules. These are empirical rules that have been determined by observing what happens when you try to dissolve ionic compounds. So this is only to determine the solubility of ionic compounds. And it tells you, if compounds contain, nitrate, acetate, chloride, bromide, iodine, or iodide or sulfate. Yes, these would make soluble ionic compound, and then you need to pay attention to the exceptions, and the exceptions would indicate insoluble compound. And the bottom part shows you the ions that would make typically insoluble compound, like the sulfide, carbonate, phosphate, and hydroxide. But there are also exceptions. And in the exceptions, you will always find the alkali metal, which are the group 1A metals. They always make soluble compound. Another exception that is always there is the ammonium. NH4 plus always makes soluble compound. So these would be exceptions and would be soluble. So that's to determine the solubility of ionic compound. Next point is to predict the effect of temperature or pressure on a solution. So when a solid dissolves in a liquid, the effect of temperature is that if you increase the temperature, you will be able to dissolve more of the solid. So solubility of a solid increases as you increase the temperature. Solubility of a solid in a liquid increases with temperature. It is the contrary for a gas. A gas solubility will decrease when you increase the temperature. So you can put less gas in a liquid when the temperature is high. You can put, for example, more oxygen into water when the temperature is cold. So it favors cold water for fish, for example. So remember how the behavior is opposite for solids versus gases with temperature. The effect of pressure on solid is null, which means there is no effect of the pressure on a solid dissolving in a liquid. It doesn't matter if you have a high pressure or low pressure above the liquid. However, for a gas, pressure matters. If you have a gas compressed over a liquid, you will be able to dissolve more of the gas into the liquid. If, however, the pressure is very low above the liquid, this will decrease the solubility of the gas into the liquid. It's like the gas, when you put it in pressure above the liquid, it's like you are pressuring it into the liquid. You can put more of the gas into the liquid if you have high pressure above the liquid. All right, so that's the effect of temperature and pressure on solid or gases dissolving in a liquid. Okay, so next you need to be able to calculate the concentration of solutions. So there are different formulas we've covered: the volume percent, the mass per volume percent, the molarity, and we also learned how to calculate concentrations via dilution. So let's look at the reference packet to know where to find these formulas. So it is page 1 of the reference packet. Page 1 of the reference packet, the bottom half has the formulas for the mass per volume percent, which is grams of solute over milliliters of solution times 100. So it's very specific here for the units. It's grams for the solute and milliliters for the solution, the volume of the solution, times 100. Whenever you have a percentage, you should multiply by 100. And then the unit is a percent. Volume percent, again, volume of solute over volume of solution times 100. Here, as long as the two units for the volume of solute and volume of solution, they should match. As long as they match, then it can be anything, right? It can be milliliters, both of them in milliliters, or both of them in liters, both of them in cubic centimeters. As long as they are the same, you can use them in the formula and times 100. Again, the unit would be percent. Molarity is more particular. It's moles of solute over liters of solution. And again, here, the units are very specific. It's units of moles of solute over liters of solution. Molarity is not a percentage, so it's not multiplied by 100. So don't multiply by 100 there. And so the unit is capital M. Capital M represents a unit of moles per liter, right? You need to see molarity as moles per liter. And all of these units, of mass per volume percent, or molarity, can be used as conversion factors because they give you an amount of solute in a given amount of solution. So that can be written as an equality and then a conversion factor. The dilution formula allows you to find the concentration of solution you dilute, or to find, volumes, how much of stock solution volume you should get to and dilute to get a given new concentration, right? So the ones refers to the initial solution and twos to the final solution. So one's for stock solution and two for diluted solution. And so typically the first concentration is high and the volume 1 is small. And then because you dilute by adding solvent, the volume 2 is large compared to volume 1, and the concentration 2 is small compared to concentration 1, because you're diluting. All right. So next in chapter 8, we learned about colligative properties. So it's those properties that are dependent on the number of particles dissolved in the solution, and they don't depend on the identity of the solute. And so they have an effect on the boiling point and melting point, those particles dissolved. They have an effect on the melting point of the solution and boiling point of the solution. So there is the boiling point elevation and freezing point depression. So let's look at the PowerPoint slides for that. So colligative properties are properties that depend on the concentration of the solute and not its identity. So the number of dissolved solute particles affects the properties of the solution, but the identity of the solute does not matter. So let's look at the boiling point elevation, and here, boiling point elevation. So a liquid solution that contains a non-volatile solute has a higher boiling point than the solvent alone. And this would be given to you if you have a problem on that. So how do we calculate the new boiling point of a solution that contains a non-volatile solute particle? So for 1 mole of any non-volatile solute particles, it raises the boiling point of 1 kilogram of water by this amount, 0.51 degrees Celsius. So if you have 1 kilogram of water and then 1 mole of non-volatile means, you know, for example, any kind of ionic compound would fit that description, you know, as long as it's not an organic solvent that is volatile, that would work. So 1 mole of any non-volatile solute particle in 1 kilogram of water would raise the boiling point by 0.51. And because water has a boiling point of 100 degrees Celsius, so that means per mole you would increase the temperature by 100.51 degrees Celsius. For every mole, you increase by 0.51. So 1 mole would increase to 100.51, 2 moles would be 101.02, etc. So that's how we get the new boiling point of a solution that contains solutes. And for the, let's look at the freezing point depression. So that's decreasing the melting point or freezing point of solution when you have also solute in there. The freezing point depression, it's when a liquid solution that contains a non-volatile solute has a lower freezing point than the solvent alone. So this is used, for example, to spread, for example, this is used by spreading salt on the roads where there is a lot of snow, because the salt with the water will create a solution and that will decrease the freezing point. So it will remove the ice on the road. So to know by how much, it's 1 mole of any non-volatile solute that lowers the freezing point of 1 kilogram of water by this amount, 1.86 degrees Celsius. Because the freezing point of water is 0 degrees Celsius. So for every mole of, for example, salt in 1 kilogram of water, you would decrease by 1.86. So that means it would be negative 1.86 degrees Celsius for 1 mole of salt, for example, in 1 kilogram of water. And if you had another mole, then you multiply the 1.86 by 2, etc. So that's the freezing point depression. Osmosis is also a colligative property, right? So you need to be able to describe the process of osmosis and how it relates to biological membranes and dialysis. So understand what is osmotic pressure and then classify solutions as hypotonic, isotonic, or hypertonic to a reference solution. So let's look at the chapter 8 slides for that. So you need to remember that osmosis is the passage of solvent, and usually it's water, across a semi-permeable membrane. So you have to have a semi-permeable membrane separating two solutions. And so the water will move from a solution of low solute concentration to a solution of higher solute concentration. It's like if water is trying to dilute the concentrated solution, and by leaving the low solute concentration, it tries to concentrate it, right? So it's a way of trying to equalize the concentration across the semi-permeable membrane. The semi-permeable membrane only allows the solvent, usually water, to go through. The solute cannot go through the semi-permeable membrane. So that's why it's the water who moves to try to equalize the two concentrations. So that's osmosis. And then from there, we can classify solutions as hypotonic, hypertonic, and isotonic. So the study guide was mentioning osmotic pressure. So osmotic pressure is the pressure of the excess fluid, when water moves from one side to the other of the semi-permeable membrane. This changes the level of the liquid on both sides of the semi-permeable membrane. So it will increase the level where there is more solute and decrease the level where there is less solute. And the difference in the level of liquid creates a pressure, right? Just due to the gravity by the difference in level of liquid, it creates a pressure that is due to gravity. And so this pressure is what we call the osmotic pressure. And so a more concentrated solution will exert a higher osmotic pressure than a low concentration solute. So now we can classify solutions that are surrounding, for example, a cell. You know how cell membranes can be viewed as semi-permeable membranes. They allow water and very small molecules to go through. Typically, non-polar molecules can go through because the membrane inside it's non-polar. Ions, for example, cannot go through. They have to go through ion channels. And so we can classify the solution that surrounds a cell, for example, a blood cell. We can classify that solution as isotonic if the osmotic pressure is the same on both sides of the semi-permeable membrane. That means they have the same number of solute particles dissolved in them. And so typically you would be given those values that are values for solutions isotonic to the body. An hypotonic solution would have a lower osmotic pressure than body fluids. So hypotonic concentration would be a low solute concentration in the solution compared to the solution inside the cell. So that would mean the water would move in the cell to try to dilute the concentration inside the cell. So that's why here the cell is swelling and could eventually burst. And so that's the effect of an hypotonic solution to a cell, a biological cell. And an hypertonic solution is a solution that has a higher osmotic pressure than body fluids. The concentration of the particles outside the solution, outside the cell, in the solution in the beaker is higher than the concentration inside the cell. So water then will move out of the cell, because it's more concentrated outside the cell. So water will try to dilute the solution surrounding the cell, and that will make the cell shrink because it will lose water. So that's the effect of an hypertonic solution on a cell. So that is all for chapter 8. So next in the study guide, it's chapter 6. Chapter 6 is on energy changes, reaction rates, and equilibriums. So first, you need to know the difference between kinetic and potential energy. So kinetic energy is energy associated to motion. So for example, thermal energy is a kinetic energy because this is the energy of motion of the particles, due to, having a temperature, the positive temperature. So the kinetic energy is energy due to motion. Potential energy is energy due to position. So that can be due, for example, to a higher elevation. So position that is higher up will have more gravity pulling on it. So that will give it energy, and that would be a potential energy, for example. In the case of chemical bonds, we call that chemical potential energy. It's bonds, it's energy that is stored in bonds. So that's, potential energy there. There's energy stored in bonds. So you need to be able to convert energy from one unit of energy to another. So remember how there is different kinds of units of energy. So let's look at the reference packet for that. So page 1 of the reference packet, the top left corner is for chapter 6 stuff, right? So reference packet, you have the temperature equations. Heat is Q equal M delta T SH or MC delta T. C is the specific heat capacity. But here below you have energy units. So 1 calorie with the lowercase c is equal to 4.184 joules. 1 kilocalorie would be 1,000 calories. And then remember how there is a different calorie with a capital C calorie, and this is called a nutritional calorie. And 1 nutritional calorie is equal to 1,000 lowercase c calories. So of course, nutritional calories are used in nutrition, or to calculate energy of food. So to calculate the energy of food, you can use this table that gives you the amount of energy per gram of carbohydrate, or per gram of fat, or per gram of proteins, because depending on the type of food, they don't have the same amount of energy per gram. So you have the values in kilocalories or kilojoules. So that would be where you would do that. Here, notice how there is also the equilibrium constant formula, which is what you learn in chapter 6. The equilibrium constant corresponds to the concentration of products over the concentration of reactants. And we will see how in more details it becomes, concentration of C to the exponent C times concentration of D to the exponent of D, divided by concentration A to the exponent A, and multiplied by concentration B to the exponent B. We'll look at that when we are reviewing about the equilibrium constant. All right, so you saw how energy content of food can be calculated using the data given in the reference packet. So in chapter 6, we learn how to classify reactions as exothermic or endothermic, depending on the energy of reaction. So delta H represents the enthalpy change, but it's also called the energy of reaction. So it's both, right? So delta H, enthalpy change, is positive for an endothermic reaction and negative for an exothermic reaction. So you need to be able to say if a reaction is exothermic or endothermic just by being given the delta H, and if it's a negative value, it's exothermic. If it's a positive value, it's endothermic. Let's look at energy diagrams. You need to know what is the activation energy, the enthalpy change, is heat absorbed or released. So what the diagram means, this is important to understand those diagrams. So this slide 25 of chapter 6 shows you the 2 types of energy diagram you can have. So on the left, it's for the exothermic reaction. On the right, it's for the endothermic reaction. So the y-axis represents the energy level. The x-axis represents the reaction coordinate, or basically time. And so URS starts with the reactant on the left. And so the dotted line represents the energy level of the reactant combined together. And then you have this blue curve that moves up. And the difference between the transition state, which is the top of the curve, it's when reactant have their bonds broken, and it requires a lot of energy, right, to break the bonds. So that's why you need this transition state where the energy is high. And then when bonds are forming again, the energy lowers, and you get the product. Because when you form bonds, it releases energy to the outside. So the difference between the energy at the transition state and the energy of the reactant is the activation energy, right? The EA is the activation energy. That's the difference between the top of the curve and the energy of the reactant, the initial energy. And so you can view that as an energy barrier. You need to overcome this energy barrier before you can get the product. So if you do not have enough energy, the reaction will not happen. You need to have at least this amount of energy to have the reaction happening. So this is called energy of activation. It activates the reaction. And then if you have an exothermic reaction, the energy of the product is lower than the energy of the reactant. So products are more stable, they have less energy, so they are more stable. And this means that you will have a difference of energy at the end versus at the beginning that will be negative, because the difference in energy between the reactant and the product is delta H, and delta H is energy, enthalpy of product minus enthalpy of reactant. And so because enthalpy of product is a lower number than the enthalpy of reactant, so that's why you get a negative value, right? The minus enthalpy of reactant makes this a negative value. So exothermic reactions will have a negative delta H. And so the delta H is the net amount of energy difference between the beginning and the end, so between the product and the reactant. So you see how in an endothermic reaction, typically the energy of activation is very large. And that's because the products are also higher up in energy. So these reactions are less spontaneous than the exothermic reactions. Exothermic reactions have a smaller amount of energy activation and they happen readily. The endothermic reactions need more energy. You need to provide the difference of energy between the reactant and the product, because you start with a lower amount of energy and you will end up with a higher amount of energy. The product have a higher energy. So this difference in energy between the product and the reactant will have to be provided. So that's why it's an endothermic reaction. You need to provide the energy. The system, the reactant will have to absorb that energy to be able to become product. And first of all, they will need to overcome the activation energy, go through the transition state, and then they can get into products. So because the delta H is in enthalpy of product minus enthalpy of reactant, enthalpy of product is larger. So that would make it a positive enthalpy change, right? So that's why it's delta H is positive in this case. So that's what you need to retain out of the energy diagrams. So next, you need to be aware of the factors affecting the rates of reactions, which are the concentration, the temperature, and the use of catalyst. So let's look at how these affect the rate of reaction. So for any reaction, the rate of reaction will increase with an increase in temperature. Why? Because increasing the temperature increases the average kinetic energy of the molecules. And so that gives them more of a chance to overcome the activation energy of the reaction. And so you have more chances for, overcoming this energy of activation and getting to product. So increase in temperature is increasing the rate. An increase in the concentration of one of the reactant, or both, or one at least, will increase the number of collisions. You know how reactants need to collide, because they keep moving around, and they move faster if they have more kinetic energy. So then they collide, and they have to have the correct kind of collision for the reaction to happen. So if you increase the number of collisions, you increase the number of chances to have a proper collision, and then to overcome the energy of activation and get the product. Adding a catalyst is also increasing the rate of reaction, because it lowers the energy of activation without affecting the energy of the reaction, the delta H. So it lowers the energy of activation, and that's how they work. A catalyst is recovered unchanged in a reaction. It does not appear in the reactant side or in the product side. It's typically written above the arrow of the chemical equation. So this shows how the energy of activation is lowered for catalyzed reaction versus a non-catalyzed reaction. A catalyzed reaction, will have a lower energy of activation. So of course, more molecules will have the chance to have that amount of energy, and then, can become product. So that increases the rate of the reaction. But notice how the change of enthalpy, or the enthalpy change, stays the same, because the level of energy of the reactant and the level of energy of the product stays the same. It's only the transition state that is lowered. So next, you need to know about equilibriums, how to find the equilibrium constant expression, so how to write it from a given chemical equation, what's the meaning of the magnitude of K, and then know how Le Châtelier's principle predict the effect of a change on a system. So let's look at an example to explain that. So when you have a reaction that is an equilibrium, you recognize that by the fact that there is a double arrow. So here, a generic form of an equilibrium would be like coefficient A, formula A, plus coefficient B, formula B, gives coefficient C, formula C, and coefficient D, formula D. And there is a double arrow between them. There is a forward reaction and a reverse reaction. And so the amount of reactant relative to the amount of product at equilibrium is unique for each reaction at a given temperature. So there are tables with Kc values given for specific reactions. And it doesn't matter how you start. If you start with only a reactant, more or less concentrated, or if you start with products more or less concentrated, when you have a given equation or a chemical reaction that is an equilibrium, it will always go to that equilibrium, and the same equilibrium for a given reaction. And so that's why we have tables with K values. And the K value is obtained by writing the concentration of the product multiplied together, divided by the concentration of reactant multiplied together. But it's more specific than that. It's, for example, here using the generic form, it's the concentration of C, one of the product, multiplied by concentration of D, the other product. But there is also exponent. If you have a coefficient in front of the compound C, this coefficient will be an exponent for the concentration C, and the coefficient D for in front of compound D will show up as an exponent for the concentration D, right? So this is important to not forget those exponent value that comes from the coefficient in the balanced chemical equation. So that's why it is important to have to start with a balanced chemical equation that has the lowest coefficient allowed for that reaction. And so here the reactant would be concentration A to the power A, if you have a coefficient A, times concentration of B to the power of B, if you have a coefficient B in front of the formula B, right? So remember how brackets are used to symbolize concentrations in molarity. So equilibrium constant are calculated using molarities. Another thing to remember when you write the expression of an equilibrium constant is that liquids and solids are omitted. We can look at the next slide for that. The concentration of liquids and solids are constant. The liquid would typically be the solvent. Solids, if they stay solid in solution, they would have a concentration that is the same. So therefore, they are omitted from the equilibrium constant. So you would not write, for example, the concentration of a solid or the concentration of water as a liquid. So what is the meaning of the equilibrium constant, the magnitude of the equilibrium constant? So when you have a K that is much greater than 1, and here means more than, not just 1, but like 10, more than 100 even. So really greater. That means the concentration of the product is larger than the concentration of the reactant, right? Because the product are in the numerator, reactant are in the denominator. So this means you have a lot more product. So that means the equilibrium lies to the right and favors the product. So it would be an equilibrium, for example, that would have, 99% of product and only 1% of reactant, for example, right? Equilibriums can be that, lopsided, yes. When you have a K that is much less than 1, that means the numerator is small compared to the denominator. So that means this time it's the concentration of the reactant that are much larger than the concentration of product. So if you have much more reactant, that means the equilibrium lies to the left and favors the reactant. So that's how you use the K value. And then if you have a K value that is around 1, and be careful here, around 1 means 0.01 to 100. So it's quite a wide range around 1, because the K value can be very, very small or very, very large. So around 0.01 up to 100, it's considered, similar. So the concentration of product are similar to the concentration of reactant. And that means the equilibrium is a real equilibrium, if you will, in the sense that you have both reactant and product present in similar amount at the same time, right? So you can see it as something more balanced, where you have both reactant and product there, and you cannot ignore one or the other. So now let's look at Le Châtelier's principle and review what are the effects of changes on a system, on an equilibrium. What's the principle saying? So Le Châtelier's principle states that when a stress is placed on a reaction at equilibrium, the system responds by changing the rate of the forward or reverse reaction in the direction that relieves that stress. So basically, Le Châtelier's principle says that when you are putting a change on an equilibrium, the equilibrium will try to retrieve its equilibrium and will counteract the change. So it will act to counteract the change that you have brought upon the equilibrium. So some of the possible disturbances are concentration changes, temperature changes, pressure changes. So we'll focus on concentration changes and temperature changes. Pressure changes would only affect reactions where you have gases. But we will focus on concentration change and temperature change. So, for example, if you're adding a reactant of an equilibrium, because you're adding this reactant, this will make the equilibrium try to consume the reactant because you're adding more. So the equilibrium, to counteract that addition of reactant, will try to consume it. And so it will favor the product. Removing a reactant would do the reverse. The equilibrium will try to replenish the reactant, and so it will favor the reactant. So move to the left. Same with adding a product. If you're adding a product, the equilibrium will try to remove the product, so it will favor the reactant. And if you're removing a product, and this is used a lot actually in the industry, because typically you try to produce something. So by removing a product from the equilibrium, you favor the product, the production of product, because you're removing it. So the equilibrium tries to replenish the product. And so it favors the product. So this way you are able to push the equilibrium towards the side that you want by playing with those factors. Another factor is the temperature. So if you increase the temperature, so the effect will depend if you have an endothermic reaction or an exothermic reaction. If you increase the temperature for an endothermic reaction, this will favor the product, because an endothermic reaction needs energy to happen, right? It needs to absorb energy from the outside. So increasing the temperature provides that energy. So it will favor the equilibrium towards the product. But if you have an exothermic reaction that produces heat already, increasing the temperature does not favor production of heat even more. Actually, the reaction will try to go backward and favor the reactant. So this would favor the reactant in an exothermic reaction. And so decreasing the temperature in an endothermic reaction would not be favorable for the product. It would favor the reactant, because remember, the reverse of an endothermic reaction is an exothermic reaction. So if you're decreasing temperature, this does not favor the endothermic reaction, so it favors the reactant. And if you decrease the temperature and you have an exothermic reaction that produces heat, then the equilibrium will favor the product to produce heat, because you are decreasing the temperature. So the equilibrium will try to increase the temperature by producing heat. Counteract the change you've made to the equilibrium. So that's the idea of the Châtelier's principle. It's always trying to counteract the change that you've made. So chapter 9 now. Chapter 9 is on acids and bases. So first of all, you need to identify and write Brown-Châtelier acid-base reactions. And so you need to remember the acid is the proton donor, the H+ donor. So an acid will donate its proton. And the base is a proton acceptor. So the base will accept the proton. So in an acid-base reaction, you always have an acid and a base. And there will be a transfer of the proton from the acid to the base. And so you get the conjugate acid and the conjugate base. So the conjugate acid is what the base becomes, because the base, by accepting the proton, becomes the conjugate acid. Now it's an acid because it accepted that proton. And the acid becomes the conjugate base because by donating its proton, now it's lacking a proton, and so it's the conjugate base. So you want to identify those properly. Discuss how water acts as both an acid and a base. So we can look at water dissociation reaction. So if we have two molecules of water and one will act as an acid and the other as a base, because water is an amphoteric substance, it can act as both an acid and a base, a Bronsted-Lowry acid and a Bronsted-Lowry base. So the water as an acid will lose a proton or donate its proton to the base. So the acid here, by loss of a protons, becomes OH minus, because H2O minus H plus becomes OH minus. So the conjugate base of the acid, water as an acid, would be OH minus. And then the base, when it accepts the proton, becomes the conjugate acid H3O plus, right? The lone pair on oxygen gets a bond with the H plus. And so now it's positively charged because of the proton being positively charged. So you see how water, two molecules of water, will dissociate into the hydroxide ion and the hydronium ion. And so when you write the equilibrium constant for this, you get the concentration of the product over the concentration of reactant. And here the product are H3O plus, so concentration of H3O plus times the concentration of OH minus. The exponents are 1 because, you know, the coefficients are 1. And then in the denominator, you would have the concentration of water. However, water here is a liquid, it's the solvent, so you do not include the water as a concentration in the denominator. Remember how we omit the concentration of liquids and solids in equilibrium constant. And so this is now known as Kw, or the constant, the ion product constant of water, Kw for water. And it's H3O plus times OH minus. And it is known to be equal to 1 10 to the negative 14, because for a water at 25 degrees Celsius, both hydronium concentration and hydroxide concentration ion are 1 10 to the negative 7 molar. So multiplied together, it's 1 10 to the negative 14. So Kw has this value for all aqueous solutions at 25 degrees Celsius. So it is always true. So this will be used, this ion product constant for water will be used to calculate the concentration of H3O plus when you know OH minus, or vice versa, you will calculate the concentration of OH minus when you know H3O plus. You can find this in your reference packet as well. So you can see that there is a point here that says use Kw, which is concentration of H3O plus times OH minus, equals 1 10 to the negative 14 to determine the concentration of H3O plus or OH minus. So that's what I was just explaining. And so in your reference packet, you can retrieve these. So page 5 of the reference packet is where you will find the, references for the acid base. So here you have a table of relative strengths of acids and their conjugate bases. The formulas are down here, and the ion product constant of water is found here. And there is a roadmap here showing you how, if you have OH minus and you are looking for H3O plus, you need to take the Kw over OH minus, and that will give you H3O plus. And vice versa, if you have H3O plus and you're looking for OH minus, you do Kw over H3O plus and you get OH minus. So that's part of the formulas here. So you need to be able to calculate the acid dissociation constant Ka or the base dissociation constant Kb given equilibrium concentrations. So for this, you need the balanced chemical equation of the dissociation of an acid or a base. And then you need to be able to, using the Ka or Kb values to determine the strength of an acid or a base. So let's look at that in more detail. So for the reaction where an acid dissolves in water, so this is the reaction that shows the dissociation of the acid in water. So HA is the general form of an acid because you have H as first element, so that indicates an acid. Typically, it's a gas dissolved in water, and that's an equilibrium that gives H3O plus, because the water here is the base and it will accept the proton from the acid, and then the acid becomes A minus with a lone pair, right? So the following equilibrium constant can be written because it's concentration of product over concentration of reactant. Then it's concentration of H3O plus times concentration of A minus, the two product, divided by concentration of the acid, HA. And remember how H2O is omitted from the equilibrium constant because it's a liquid. So this is the acid dissociation constant. So sometimes you would be given values for those concentrations. So you need to plug in the values. They should be in molarity. And that will give you a Ka value. And so when the Ka is very large, right, the larger the Ka, the stronger the acid. Right, because a large value would indicate, let's see if I can write here, would indicate, a large value would indicate that the concentration of product is much larger than the concentration of reactant, right? Mathematically, that means the numerator is much larger than the denominator. So that means the concentration of product is large, and that goes with the fact that an acid dissociates completely into its ion, is a strong acid. So this confirms that would be a strong acid if you have a large Ka value. And so the same goes with a base. So a base B with a lone pair, when dissolved in water, would dissociate into OH minus. This time, because it's with a base, the water would act as an acid and donate a proton to the base. So the base becomes BH plus, and the water, by donating an H plus, becomes OH minus. So you see how this is a base because it's producing hydroxide ions. So the equilibrium constant is OH minus times BH plus over B. The base dissociation constant. And so again, the larger the Kb value, the stronger the base, because again, a large Kb value would mean you have a stronger product concentration than a reactant concentration. So stronger product concentration means the base completely dissociates into its hydroxide ion and BH plus ion. So that indicates a strong base, a base that completely dissociates in water. So that's why it's all falling together, right? So you want to be able to say that, to come to that conclusion when you see the Ka value or Kb value. So next in chapter 9, it's about pH calculations using the pH equals negative log of the concentration of H3O plus. Or if you have the pH and you're looking for the hydronium ion concentration, then it's equal to 10 to the negative pH. So it is important here to know how to do this properly in your calculator, right? So the log key and the inverse log key would be allowing you to do this. And you need to be able to classify a solution as acidic, basic, or neutral based on pH or H3O plus concentration or OH minus concentration. So Again, these formulas are found in the reference packet. So let's look at where they are. So again, page 5 of the reference packet, the bottom, that's where you have the formulas for the pH calculations. pH equals negative log of H3O plus. So you use that formula when you have the concentration of H3O plus. And so here the roadmap shows you that if you have the concentration of H3O plus and you're looking for the pH, then you use negative log of the concentration of H3O plus. If, on the contrary, you have the pH and you're looking for the H3O plus concentration, then you would use the 10 to the negative pH formula, or the anti-log of negative pH. So be careful here. The pH should be with a negative sign in front when you use this formula, right? And so it is important to note here that the concentration H3O plus should have the same number of significant figures. There are decimal places in the pH. Decimal places are digits to the right of the decimal point. So for example, a concentration with 2 significant figures, for example, 2.2, 10 to the negative 3, would give a pH where you have 2 decimals. So I'm completely making this up, but maybe 3.22, right? You need 2 decimals if you have 2 sig figs, and vice versa, right? So this is a special rule, and it's reminded here. So if you forgot, it's there. So that's for pH calculations. You can look at that in your reference packet. Otherwise, you want to be able to identify or classify a solution as acidic, basic, or neutral. For this, you need to be able to do it using the pH or using the concentration of the hydronium ion or the OH minus ion concentration. So for the pH, pH 7 is neutral, and it has to be exactly 7. pH below 7 is acidic, and pH above 7 is basic. So a pH of 7 means the H3O plus concentration would be 110 to the negative 7 molar. And that is when the OH minus concentration would be exactly the same as well. So that's when it's neutral, when you have exactly the same amount of H3O plus and OH minus. And as soon as you deviate from that, when the concentration of H3O plus is larger, so larger than 110 to the negative 7, so that would mean, you know, smaller exponents here, so 10 to the negative 2, 10 to the negative 3, etc. That would be a large H3O plus concentration, and that's acidic. When you have a small concentration of H3O plus, you know, so 110 to the negative 8, negative 10, negative 12, that would be a small concentration of H3O plus. So that would indicate a basic solution. And remember how if the concentration of H3O plus is small, then that means the concentration of OH minus is large, right? So a basic solution would have a large amount of OH minus. And an acidic solution would have a small amount of OH minus, right? If the H3O plus is large, then the OH minus is small. So you want to remember this by heart, right? This is the basic knowledge for, you know, classifying acidic and basic solutions. And so lastly, you need to be able to communicate how a buffer prevents large pH changes. So the lab can help you with that. Let's look at the slides. So a buffer is made of a weak acid and its conjugate base. And the role of a buffer is to maintain the pH to a value that depends on the buffer itself. So it's a solution whose pH changes very little when an acid or a base is added. For example, when you have no buffer like water, pure water, you start with a pH of 7. If you add either an acid or a base, the pH changes dramatically, right? And on the contrary, when you have a buffer, and if you add some amount of acid, let's say the buffer maintains the pH at 7, which is not the case for most pH, right? They have different values that they try to keep. So if you add an acid to a buffer, the pH will only decrease slightly, for example, from 7.0 to 6.9. And if you add a base to that buffer, instead, it will go from 7.0 to 7.1. So a buffer is able to maintain the pH around that value. In this case, it's 7, but it's not necessarily 7.0. And so as long as the amount of acid or bases that you add are small, it doesn't work anymore if you are adding way too much. So buffers are solutions composed of roughly equal amounts of a weak acid and the salt of its conjugate base. So you need both in large concentrations and about the same concentration. And so a buffer resists changes in pH because the added base, if you add a base to disturb the solution, it will react with the weak acid of the buffer. And if you add an acid, it will react with the conjugate base of the buffer. And that's how the buffer is able to maintain the pH, because it kind of absorbs, if you will, the added base or added acid by having its weak acid or conjugate base react to them. Again, the pH of a solution is maintained as long as the added amount of acid or base are small compared to the concentration of the buffer component. And so lastly, for chapter 9, it's not in the study guide, but you want to be able to write a reaction of acids with a strong base. So with the hydroxide base, because the strong bases are only bases that contain the hydroxide ion, OH-. And so we call these reactions neutralization reactions, where you have an acid reacting with a base to produce a salt and water, right? So the acid provides the H+ ion, the base provides the OH- ion, and they make the water, right? H+ plus OH- makes H2O. And so the anion of the acid reacts with the cation of the base to make a salt. So that's a very generic form of an acid-base reaction that we call a neutralization reaction. And this, we have been through this in another chapter before, so this shouldn't be too new. All right, so that ends the overview for exam 3. All right, so good luck on the exam. And so if you need more practice, use those odd problems from the textbook, because you have solutions in the appendix B at the back of the textbook.